Welcome to the Deep Dive, the show that cuts through the noise to get you truly well informed. Today, we're tackling a challenge that keeps, well, let's be honest, many modern software teams up at night. It's understanding what's really happening inside these complex, interconnected software systems. You know the drill: a user reports a problem, and you're left guessing which of your dozens, maybe hundreds of microservices is the actual culprit. Problems just hide across all these different layers and services, and finding the root cause. It can feel like searching for a needle in a haystack made of, well, code. But there's a leading open standard emerging to try and solve this very problem, and it's called OpenTelemetry. Now, if we've heard the name but maybe found it a bit intimidating, consider this deep dive your shortcut, your way into understanding this really powerful technology. Our mission today is pretty clear. We're going to demystify OpenTelemetry. We'll explain its core concepts, look at its practical applications, especially for us Ruby folks, and share some essential best practices for building, truly robust observability.
We've pulled from a real mix of sources for this one: official docs, technical articles, even real-world community discussions. So get ready for hopefully a well-rounded and very practical perspective. Okay, so let's unpack this. The core problem OpenTelemetry is designed to solve is pretty fundamental these days. Modern software isn't just that single monolithic app anymore, is it? It's this sprawling network of microservices, each doing its own thing, often in totally different languages. When a user clicks a button, that single request might bounce between, a dozen different services before it's actually done. So traditional single app tracing, like what you might see in an Elastic APM screenshot for just one Rails controller action. That only gives you a tiny slice of the pie. It shows what happens inside that one app, but not the whole journey, not across all of them. Which means the critical need really is for distributed tracing, being able to follow a single user request end-to-end seamlessly right across all those service boundaries. But, given how complex these systems are, what's the trickiest part about making that seamless thing actually happen?
How do you connect the dots?
Yeah, that's exactly where this coordination problem comes in. And it's genuinely fascinating when you dig into it. It's the challenge of how all these different applications, maybe one's in Ruby, another's Java, another's Node, how do they communicate and somehow stitch together a single unified view of that one transaction? And this isn't just about debugging, right? It's about seeing the invisible choreography of your microservices. Understanding why, say, a slow payment isn't just one service's fault, but maybe it's a cascading effect across 5 different ones. You need consistent trace propagation passing unique IDs between services. That's key. You need standardized export formats so all that data can actually go to a single backend system. And crucially, you need this to be language independent, vendor independent, and all without hurting performance or introducing new bugs. That's the goal.
Okay, so that's the massive challenge. And what's fascinating here, you're saying, is how OpenTelemetry steps in as the sort of elegant solution to this coordination problem. I saw one source use this surprising USB analogy, which really clicked for me. Can you walk us through that? How does that parallel help explain the big picture here?
Absolutely, yeah. The USB analogy is actually pretty good. Think about USB, right? When it first came out, maybe it felt a bit clunky. Different connector types, different versions. But despite those initial quirks, it solved a fundamental problem: hardware connectivity. Before USB, every single peripheral needed its own custom port, its own driver.
Yeah.
It was a mess. After USB, almost everything just became compatible. Plug and play, mostly.
Okay.
OpenTelemetry is aiming for that same kind of universal adoption, but for observability data. It's solving that fundamental coordination challenge. It's specifically designed as a framework, a set of tools and standards for instrumenting your code, collecting the data, and exporting telemetry data. And that includes traces, metrics, and logs. And this is really vital to understand, OpenTelemetry is not an observability backend itself. It doesn't store your data, it doesn't analyze it, doesn't visualize it. Instead, it provides the standardized tooling to get that data out of your application reliably. And its superpowers are really that it's open source, it's vendor agnostic and language agnostic. That means you're not locked into any single vendor or technology stack.
Okay, so if I'm a developer listening to this, why does this core concept matter directly to me? What's the practical impact of having this universal connector for my app's insights?
Well, fundamentally, it liberates you from vendor lock-in, and that's just a huge win, right? You instrument your applications once using the OpenTelemetry APIs and SDKs, and then you have the flexibility to send that data to any compatible observability backend, whether that's an open source tool like Aegir or Prometheus, or maybe a commercial platform like Datadog or Honeycomb. This gives you what some people call data sovereignty. You get central control over your valuable telemetry data. You decide where it goes, how it's processed securely, regardless of your backend choice. So you can switch backends with much less friction. You can compare tools side by side, maybe even send data to multiple places at once. And most importantly, you gain that holistic view of your system's behavior, that end-to-end picture that was often just impossible before.
That makes total sense. Freedom and flexibility. Okay, so that's the why. Really compelling. Now let's pivot to the how. How do you actually, get started with open telemetry? What's the easiest way to begin seeing these benefits in a real world app? Maybe thinking about Ruby examples.
Yeah, the easiest way in definitely is what we call auto instrumentation. This is really an excellent starting point because it automatically instruments common libraries and frameworks you're probably already using. Things like HTTP client libraries, database adapters, maybe web frameworks like Rails or Sinatra. You get pretty immediate visibility, often with minimal or sometimes even zero code changes in your actual application logic. The absolutely critical detail, though, is that OpenTelemetry must be initialized before any of these instrumented libraries are loaded or used. So, for instance, in a Ruby on Rails application, you typically put this setup command in an initializer file, like config initializer sopentelemetry.rb, to make sure it loads nice and early in the boot process. You'll usually install the core OpenTelemetry SDK gem, and then there's often a helpful convenience gem, like OpenTelemetry instrumentation all in Ruby, that bundles instrumentations for loads of common libraries.
Okay, auto instrumentation sounds like a fantastic way to get up and running quickly, almost too easy. But what about when I need to track something really specific, like a critical business process inside my own code, not just a standard library call? Is that where manual instrumentation comes in? And are there any common pitfalls or things to watch out for when you start doing that?
Exactly. Manual instrumentation is your tool for when auto instrumentation isn't enough or doesn't capture the specific context you need. This is where you actively write code using the OpenTelemetry API to create specific spans for your custom logic, maybe wrap critical business paths or add unique context as attributes. You can also use it to capture custom metrics derived from your application's behavior or mark important state transitions within a process using something called span events. A common pitfall I've definitely seen and probably done myself is forgetting to properly close the spans you manually create. It's absolutely crucial to make sure spans are always closed, even if exceptions happen within that block of code. So thinking about using constructs like begin.ensure.end in Ruby or try.finally in other languages is really important to guarantee spans get finished. Honestly, the most effective strategy usually combines both. Start with auto instrumentation for that broad baseline coverage, and then strategically add targeted manual instrumentation where you need deeper business-specific insights.
Got it. So you mentioned spans and attributes. When we're talking about these traces, what are the kind of fundamental building blocks we're working with?
Right, connecting this to the bigger picture. The core components you're manipulating are mainly spans and attributes. Think of a span as representing a single logical unit of work within a trace. It could be an HTTP request, a database query, or a specific function call you've manually instrumented. Each span has a start time and a duration. Attributes are then key value pairs that you attach to these spans to add rich descriptive metadata. This gives context. OpenTelemetry defines standard semantic conventions for common attributes like http.method set to git or db.system set to PostgreSQL, but you can and should add your own custom attributes relevant to your application, maybe like user.ad or cart.itemCount. And the real magic, the thing that actually ties these distributed traces together across different services, is context propagation. This is the mechanism by which trace identifiers, trace seed, and the current spans identifier spannet, are passed along from one service to the next as a request flows through the system. For HTTP requests, this usually happens automatically via HTTP headers. OpenTelemetry typically uses the W3C trace context standard, which is now widely adopted, defining headers like trace parent and trace state. The instrumentation libraries often handle injecting and extracting these for you. There's also a related feature called baggage. This allows you to propagate arbitrary key value pairs, not just trace IDs across service boundaries. So you could propagate something like a customer.tier or experiment.group along with the request, making that information available in downstream services traces without them needing to look it up again.
Okay, that context propagation sounds like the secret sauce. And for our Ruby listeners, what does this setup actually look like? If they follow the steps, install the gems, configure the initializer, how do they actually see it working initially?
Yeah, so for Ruby, like we said, you'll install the necessary gems. OpenTelemetry SDK is the core one. and probably open telemetry instrumentation all to get started easily. Then you configure the SDK, usually in that initializer file, config initializers opentelemetry.rb. You'll typically tell it which instrumentations to use, maybe c.usil to begin with, and configure an exporter. For just getting started and seeing something, the easiest exporter is the console exporter. You can often enable this just by setting an environment variable like oteltrace exporter console before you run your Rails server or script. When you run your app and make a request, like hitting a controller action, you'll then see detailed output printed directly to your console for each span that was generated. This output will show you the span name, its unique trace seed and spanid, its parent span's ID, linking it in the trace, start and end times, and importantly, all the attributes associated with it, things like http.method, GT, http.statuscode, 200, service.name, or your app dat name. It gives you that immediate feedback that instrumentation is active. Now, beyond your application itself, there's another really vital component in many OpenTelemetry setups, the OpenTelemetry collector. You should think of the collector as a kind of central hub, or maybe an agent, that sits between your applications and your actual observability backend. It's designed specifically for receiving, processing, and exporting telemetry data. Using a collector offers a whole bunch of benefits. It can buffer data if your backend system is temporarily unavailable, preventing data loss. It can centralize authentication credentials so your apps don't all need backend keys. It can also perform pre-processing tasks like filtering out noisy data, adding common attributes, or, really importantly, redacting sensitive information, maybe stripping passwords out of a db.statement attribute before that data leaves your network perimeter. Plus, it can route data to multiple destinations simultaneously. Maybe you want to send traces to Jaeger and metrics to Prometheus, or perhaps you're evaluating 2 different commercial vendors and want to send data to both for a while. The collector handles that routing. It also reduces the load on your actual applications because they just fire off the telemetry quickly to the collector, and the collector handles the potentially more intensive work of batching, retrying, and exporting to the final backend.
That collector sounds incredibly powerful, especially that idea of pre-processing sensitive data before it leaves your control. That seems huge. But I can imagine some listeners thinking, okay, great, another component to deploy and manage. Isn't that just adding more complexity? How do you usually frame the value proposition there?
That's a totally valid concern, yeah. It is another piece of infrastructure to manage. But the argument is that the collector actually reduces complexity and brittleness downstream and significantly increases the reliability and flexibility of your whole observability pipeline. It insulates your application code from backend issues, from needing complex export logic, from handling retries and batching efficiently. It centralizes that logic, and it gives you that crucial control point for managing data flow, security, and cost. So while it's an upfront investment to set up, it usually pays off significantly, especially in larger or more complex environments. You can deploy it in different ways too often as an agent running alongside your application instance, like on the same host or as a sidecar container, or as a central gateway service that aggregates data from many sources, or even in a hierarchical pattern combining both approaches. And then finally, just to complete the picture, there are the exporter. These are the specific components either within the application's SDK or within the collector that are responsible for actually sending your collected telemetry data to a specific backend system using the correct format and protocol for that backend. Common exporters exist for the standard OpenTelemetry protocol, OTOP, and also for older formats like Jaeger and Zipkin, plus many vendor-specific formats.
Right. So just to recap that part, getting started with auto instrumentation is really quick, gives you that immediate baseline visibility. Then you can layer in manual instrumentation for the deeper business-specific stuff. And the collector acts as this optional but highly recommended central hub for processing and routing, giving you more control and resilience. Okay, so we're collecting all this potentially massive amount of data now. How do we make sure it's not just, a fire hose of noise? How do we ensure it's actually useful, reliable, and trustworthy? What are the key principles or best practices that OpenTelemetry itself guides us by for building really robust observability?
That's a critical question, and it leads into best practices around managing the data and the instrumentation itself. A core philosophy in OpenTelemetry, especially around error handling, is really important to grasp. It's explicitly designed to not significantly interfere with your application's normal operation. The priority is almost always lose telemetry data rather than cause the application itself to fail or misbehave. This translates into specific rules for the OpenTelemetry libraries themselves. For example, API methods generally must not throw unhandled exceptions just because you, the user, used them incorrectly, like passing null when a string was expected. They should often return safe default values or no-op objects instead. Now, it is generally considered okay for OpenTelemetry to fail fast during initial configuration, like if you provide a totally invalid endpoint for an exporter, the app might fail to start, which is probably what you want. But crucially, once the application is running, failures within the OpenTelemetry components themselves, like an exporter failing to connect to its backend, must not propagate out as unhandled exceptions that could crash your application process. The telemetry system needs to handle its own failures gracefully. OpenTelemetry often achieves this using those no-op or default objects we mentioned, basically. Harmless placeholder objects that do nothing, so that if an error happens internally, like failing to create a real span, the application code calling the API still gets something back and doesn't crash with a null reference exception. Good OpenTelemetry libraries are also encouraged to expose their own internal metrics and maybe even traces for self-diagnostics. Things like how long exporters are taking to upload data, or how many items are currently buffered in an export queue. And if an internal error is suppressed, like that failing export, the library should still log it somehow using standard logging mechanisms for that language so you can find out about it. They often allow you to configure custom error handlers too.
That's a really strong principle. Prioritize application stability above all else. Makes sense. Now, when it comes to managing all those attributes and contexts we talked about, adding to spans, how do we keep that data consistent and useful without just creating this massive, noisy, expensive data set?
Yeah, consistency and relevance are absolutely key here. First, you should really try to follow the established semantic conventions. OpenTelemetry maintains specifications that define standard names and expected values for attributes related to common operations. HTTP requests, database calls, messaging systems, RPCs, and so on. Using these conventions like http.method, http.statuscode, db.system, db.statement makes your telemetry data consistent and interoperable. It means dashboards and alerts built into backend systems are more likely to work out of the box, and it makes it easier to understand traces that span services written in different languages because they're all speaking the same attribute language, so to speak. For your own custom attributes, the key is to use descriptive and, most importantly, consistent naming across your services. Don't call it userid in one service and userID in another and shopperID in a third. Pick a convention and stick to it. And then there's relevance. You really need to be mindful of only including information and attributes that is genuinely useful for understanding or debugging that specific unit of work. You generally want to avoid stuffing huge blobs of data, like entire request or response bodies, into attributes. Think summaries or key identifiers. Critically, you should avoid putting metrics or logs as span attributes. Spans describe what happened and why. Metrics aggregate numerically. Logs record discrete events. Use the right tool for the job. And be very cautious with high cardinality attributes, attributes that can have many, many unique values, like maybe a requested from an external system, or potentially even userid if you have millions of users. While sometimes necessary, using high cardinality attributes widely can significantly impact the storage cost and query performance in your backend observability system. Be strategic about where you use them.
Right, being strategic, not just logging everything. That makes sense. Especially the high cardinality point. I could see how that would explode costs. But even being strategic in really massive high traffic systems, collecting all the trace data for every request can still be incredibly expensive, right?
Yeah.
Both in terms of performance overhead and just storage costs. How do you balance that need for comprehensive visibility with the practical realities of data volume and cost?
This raises a really important question, and it's where sampling strategies become absolutely crucial. It's a tough balancing act. As you said, you don't necessarily need or want to record the full trace data for every single trivial request in a super high volume system, but you absolutely do want to capture traces for errors, for unusually slow requests, or for requests hitting critical paths. It's like needing to hear every scream from your system, even if you only listen to a fraction of the whispers. Smart sampling lets you capture those critical signals without drowning in the noise or breaking the bank on observability costs. There are different approaches. Head sampling makes a decision right at the beginning of a trace, typically based on probability, like sample 10% of all traces. It's simple, but might miss important errors that happen later in the trace. Tail sampling is more sophisticated. It collects all the spans for a trace first, usually in the collector, and then makes a sampling decision based on the characteristics of the completed trace. For example, you can configure it to always keep traces that contain an error status, or traces that exceed a certain duration threshold, while perhaps still sampling only a fraction of the fast, successful traces. Tail sampling gives you better visibility into problems, but requires more resources in the collector. You also have basic probabilistic sampling, just a random percentage, and rate-limiting sampling, like don't send more than 100 traces per second to control volume during traffic spikes. A very common best practice is actually to use a combination. Maybe use probabilistic head sampling in the application SDKs to shed some initial load, but configure tail sampling in the collector to ensure that 100% of error traces, and maybe traces for specific important endpoints, are always kept, regardless of the head sampling decision. One really crucial point here, though. If you're generating metrics from your trace data, which is a powerful technique, you need to make sure those metrics are generated before any sampling decisions discard the trace data. Otherwise, your metrics derived from traces, like error counts or latency histograms, will be inaccurate because they'll only reflect the sampled subset, not the total traffic. Span metrics processors often handle this.
That's a really profound distinction, hearing every screen versus just sampling the whispers. And the point about generating metrics before sampling is critical. The real power, though, seems to come when you can actually combine these different types of telemetry data, right? Traces, metrics, logs. How do we best correlate them to get that truly comprehensive 360-degree view of our system?
Absolutely. The real power, the real aha moments in observability, often come from correlating telemetry data types, seeing how traces, metrics, and logs tell different parts of the same story. For logs, the key is to ensure that whenever possible, your application logs include the current trace seed and span it in the log context. Many logging libraries have integrations or formatters that can automatically inject these IDs if an active OpenTelemetry trace context exists when the log message is written. For instance, the Winston logger in Node.js has libraries for this. When your logs have these IDs, your observability backend can automatically link log entries directly to the specific trace and span during which they occurred. So you can jump from a slow point in a trace directly to the relevant logs, showing exactly what the application was doing or thinking at that moment. For metrics, a really powerful technique is generating key operational metrics directly from your trace data, often using span metrics processors in the collector or SDK. This allows you to easily implement things like RD analysis tracking the rate, errors, and duration, latency, for requests handled by your services based on the information already present in your spans, like status codes and durations. This gives you high-level service health dashboards derived consistently from your tracing data. And for visualization, trace data is often used by backends to automatically generate service graphs. These maps visually represent the dependencies between your services, showing how requests flow between them, and often overlaying metrics like traffic volume or error rates onto the connections. This can be invaluable for understanding your architecture and spotting unexpected dependencies or bottlenecks.
That correlation capability sounds incredibly powerful, jumping between traces, logs, and metrics for the same event. Finally, on the practical side, what about the performance impact on our applications? We're adding this instrumentation code. How do we minimize its overhead and make sure it doesn't cause problems itself?
Right. Performance optimization and resilience of the instrumentation itself are vital considerations. You don't want your observability system to negatively impact the thing it's observing. One of the main sources of overhead is exporting the data over the network. Using batching is crucial here. Instead of sending each span or metric individually as soon as it's created, OpenTelemetry SDKs and collectors typically buffer data and send it in batches. This significantly reduces the number of network requests. Configuring batch processors involves tuning parameters like the maximum queue size, the scheduled delay between sends, and the maximum batch size. Enabling compression, like using gzip for OTLP exports, is also very important. It can dramatically reduce the amount of data sent over the network, saving bandwidth and cost, especially for verbose trace data. Exporter configurations often have a simple option to enable this. It's also really important to monitor the instrumentation's impact itself. Keep an eye on the CPU usage, memory consumption, network bandwidth usage, and any potential added latency introduced by the OpenTelemetry components running within your application or as an agent collector. You need to ensure the overhead stays within acceptable limits. And finally, to prevent telemetry collection from actually impacting your application's availability, especially during backend outages or network issues, you should implement circuit breakers or similar resilience patterns. This typically involves setting sensible timeouts for export operations, e.g. don't let an export block for more than a few seconds, and configuring maximum queue sizes, max queue size in batch processors, and potentially dropping data if the queue gets too full and exports are failing. This ensures that even if your observability backend is completely down or unreachable, the telemetry system won't exhaust application resources, like memory for huge queues, or cause requests to hang indefinitely waiting for exports. Again, it prioritizes application health over capturing every single telemetry signal during a failure.
Okay, so lots of levers to pull there for performance and resilience. It definitely sounds like, with all these moving parts, configuration, sampling, correlation, performance tuning observability isn't really a one-time setup, is it?
Precisely.
It's very much an ongoing journey, not a destination. It requires continuous attention, refinement, and adaptation as your system evolves, as your traffic patterns change, and as your understanding of what's important deepens.
Right. Let's bring the discussion back then to tangible impact. We've talked a lot about the technical how-to, the components, the best practices. But how is OpenTelemetry actually being used out there in the real world? Across different industries, what kinds of concrete problems is it solving for people day to day?
Oh, it's remarkably broad now, really seeing widespread adoption. If you're running a classic Ruby on Rails application, like we mentioned, OpenTelemetry gives you much deeper insights into request lifecycles, database query performance, background job execution, things that might have been quite opaque before. In microservices architectures, it's pretty much essential. Distributed tracing is the key use case, mapping those complex service dependencies and figuring out where latency is introduced in a multi-hop request. For e-commerce platforms, it's huge. They use it for tracing critical user journeys like the checkout flow in real time, monitoring for errors or performance degradation that could cause customers to abandon carts. Understanding the exact sequence of service calls during a purchase is vital. SaaS and cloud-native applications heavily rely on it for monitoring API performance, understanding resource usage in cloud environments, like correlating traces with Kubernetes pod information, and ensuring their service-level objective, SLOs, are being met. Even in more traditional sectors like financial services and fintech, it's seeing uptake for monitoring critical transactions, ensuring correctness, and providing audit trails for compliance purposes. The ability to trace every step of a money transfer, for example. In gaming and entertainment, low latency is everything for a good user experience. OpenTelemetry helps them pinpoint sources of lag in game servers or streaming infrastructure. DevOps and CI/CD teams are starting to use it too, instrumenting their build and deployment pipelines to understand bottlenecks, optimize deployment times, and catch integration issues earlier. And even in the IoT space, it's being used to gain visibility into device health, track communication patterns between devices and back-end systems, and troubleshoot connectivity issues. It's really quite versatile.
That's an impressive range of applications, showing how fundamental this visibility is. But beyond just monitoring and debugging production issues, I read about this novel type of testing emerging, trace-based testing. This idea where you actually validate your system's behavior by checking the traces it emits during a test run. The official OpenTelemetry demo application apparently uses this quite a bit for its integration and end-to-end tests. Can you give us a compelling example, like what kind of bug could this catch that traditional tests might miss?
Yeah, trace-based testing is a really interesting evolution. And what's fascinating here is a specific anecdote that came up in the community around the OpenTelemetry demo involving an email service bug. So the setup was they had an email service, which happened to be written in Ruby, and it expected the JSON fields in the requests it received to be in snake case, the typical Ruby convention. However, one of the end-to-end tests, maybe written in a different language or framework, was directly calling this email service, but sending the JSON payload with fields in Pascal case. Now, the tricky part was the Ruby email service itself didn't actually throw an error. Its logic probably just ignored the fields it didn't recognize because of the case mismatch. So if you looked only at the trace bands generated within the email service, it looked like it processed the request successfully. But the service that called the email service received an HTTP 500 internal server error response because ultimately the email wasn't sent correctly due to the missing data. This subtle interaction, this mismatch in data format expectations between two services was only clearly visible and diagnosable when looking at the entire end-to-end trace. You could see the successful-looking spans inside the email service, but you could also see the HTTP 500 status code attributed to the span representing the call to the email service from the upstream service. It really highlights how trace-based testing, by asserting properties of the complete distributed trace, like checking for error statuses on specific spans or verifying that certain services were called in the expected sequence, can catch these kinds of cross-service integration issues that might be completely missed by unit tests focused on a single service, or even by integration tests that only check the final output without examining the internal interactions.
Wow, that's a brilliant example. It really shows how traces give you this kind of X-ray vision into interactions that were previously hidden, a real superpower. Now, while OpenTelemetry clearly offers immense power, it also sounds like it's not trivial. There can be complexities, maybe a learning curve. What advice would you give to listeners who are just starting out or maybe trying to deepen their adoption within their teams?
That's absolutely true. Let's be realistic. OpenTelemetry can be complicated. The scope is huge. The documentation, while improving rapidly, can sometimes have rough edges or assume prior knowledge. It definitely requires a learning curve. And you still have to make that important decision of selecting and managing an appropriate observability backend to actually store and analyze all the data. However, the counterpoint is the incredibly strong community momentum and the really extensive vendor support across the ecosystem. It's clearly become the de facto standard, signaling its long-term viability. It's worth the investment. So, my advice is usually focused on incremental adoption. Don't try to boil the ocean. Start with auto instrumentation. Get that easy win and immediate baseline visibility for your most common libraries and frameworks. Then, prioritize instrumenting your most critical user-facing services first. That's often where you'll get the biggest bang for your buck in terms of understanding user impact. Add manual instrumentation strategically, focusing on key business transactions or complex internal logic where auto instrumentation doesn't provide enough detail. And perhaps most importantly, focus on building in-house expertise gradually. Start small, maybe with one team or one service. Learn the concepts, experiment, share knowledge internally. Don't try to roll out a massive, perfect OpenTelemetry implementation across the entire organization all at once. Iterate and grow into it.
That sounds like very pragmatic advice. Start small, iterate, focus on value. So there you have it. We've gone from understanding why your sprawling microservices desperately need this unified view to getting your hands dirty with setup, especially in Ruby, exploring core concepts like spans and context propagation, diving into the crucial role of the collector, and then really mastering the data with best practices like semantic conventions, smart sampling strategies, remembering the screams versus whispers, correlating traces, logs, and metrics, and ensuring performance and resilience. OpenTelemetry really does offer this comprehensive capability, this super tower, for truly understanding your applications in today's distributed world. By making those previously invisible inner workings of your code visible through OpenTelemetry, you're not just debugging faster or more efficiently, you're really gaining a new ability to optimize, to innovate, and to truly understand the experience you're delivering to your users. So the thought I want to leave you with is this. Imagine which hidden inefficiencies, which elusive cross-service bugs, or which performance bottlenecks in your systems right now could finally be uncovered and understood with this newfound transparency. What could you fix or improve if you could truly see everything?